because these have got horizontal components, there will presumably have to be some sort of horizontal resistance at that end as well. But the point is that you've got three equations to find these three things out with. The three equations are statically determined, right? What about this? Pin there, pin there, pin there, with some sort of loads on it. But obviously it will need vertical supports at both ends. Obviously, because it's going to do that, it will need some sort of horizontal thread. You appear at first sight to have four unknowns now, and you've only got three equations of statics. But what you do know is that that and that have got to be equal. So in fact there are only three equations. There are three equations of statics, and once you fiddle around a bit, there are basically only three things. Now, let's set up a sort of example of this one that I can do in my head. At least I hope I can do it in my head. Some more chalk, a sensible thing to do rather than drawing the fingertips.
How come Sherman didn't say anything about what questions we asked? I think he did that. I think he did hint at it.
I don't think any of you would have any bother at all getting the vertical reactions for that, would you? Well, go on then. Why should I do all of that? Vertical reactions for that.
96, 48, 48. It's 12 times 4. Huh? 42.
18, 30, 42?
Yeah. 54. What's the calculating? I think just a vertical reaction.
18, 38.
Tom is 96.
Yeah.
Each individual floors.
I've split that into 5/6 and 1/6 since it's 5/6 of the way along. I've split that into 2/3 and 1/3 since it's 1/3 of the way along. I've split that half and half since it's in the middle. I mean, alternatively, you can just write them out, write a bloody great equation out longhand if you want to. But let's assume I've got it right. I may not have got it right. What would happen if I put a hinge in there?
No, don't say that.
It would just fall down, wouldn't it?
Yeah.
So obviously you can't put a hinge in a beam. But what happens if, instead of a beam, I make an arch like that, let's say for the sake of argument, 8 meters high. And put the same loads on it. Now what we'll have is we'll have a vertical load at this end, a vertical load at this end, and because arches spread, provided we put a tie in there, even though we've now got 1, 2, 3 hinges in, it won't fall down, will it? How do you get those vertical forces? And the answer is that they're exactly the same as those. I used to find great difficulty in believing this when I was undergraduate, by the way, but they are the same. Why are they the same? Because the only other forces that, the only things we've introduced new between that and that are at the top hinge there, some sort of force and some sort of shear force at the top hinge. But if we take moments about there, let's say, for the whole system, taking moments of that would be exactly the same as we got in the B, and would give us this 54. And the effect of that, taking moments of that and that would cancel each other out, and that would cancel each other out. Internal forces do not generate any moments. So basically it's just the same as it would have been for a straightforward beam. How do I get the horizontal force? Well, I say, well, I know it's got a hinge up there. So let's have a look at the equilibrium of this bit. I now know that that's 42. I don't know what that is, but I know that these are respectively 12, 12, 24, and 24. Is that right? 12, 12, 24, 24. So if I take moments about there, that one doesn't have a moment. There's a moment due to that, moment due to that, moment due to that, moment due to that. And there is a moment due to that.
No, that's all equal forces. This is added into any. This is unequal forces.
And what do I know when I add all those moments up? It's got to be 0 because it's a hinge. Yeah. So that's how you find this force. And I'm sorry to sort of labour the first year thing, but you know, if you can't do your first year statics, you're going to be in dire trouble. So basically a 3-pin arch is just like a beam with an extra hinge, and that extra hinge is compensated for by a horizontal force. And that's what I've done in the notes. So, if you look at the next page in the notes, the actual solution, I've said if I take moments about A for the whole system, I'll get the vertical reaction at the right-hand end. If I take moments about the other end, H, for the whole system, I'll get the vertical force at the left-hand end. With any luck, if I add them up, they should come out as the same in the vertical load. If I then take moments about the top hinge for either side, I should be able to get the horizontal force. And what I've done in the notes is I've worked that one out. Quite separately, I've worked that one out and shown that they both give the same answer. Now, you ought to be able to do that. If you could in the exam, you got yourself 8 marks without knowing anything about timber. But now what we've got is we've got the forces. Now the reason for this is that, and I probably said in the question where I want you to work it out, at a point just below C. So what I've said in the question is, what happens if you look at the equilibrium of that piece? That's A, B, C. I'll draw it nice and big. There it is. A, B, and C. And I know that what's on it is a vertical force of 42 to hold the whole thing up. A horizontal force of 18.5, because I just might work that out. And vertical forces of 12, 12. I don't think I've got, oh, I have. No, they aren't. They're 7. No, sorry, we'll stick to the one in the notes. Sorry, I'll transfer it to the one in the notes. What were they? 7. 7. Vertical reaction of 21.6. Right. Now, what I'm interested in is what the axial force of the member is and what the shear force of the member is. So the first thing I do is I have a look at the horizontal equilibrium. To cope with that, I would need this half to produce a force of 18.5. To cope with these, an upward force of 21.6 and two downward forces of 7, I would need a force of, that depends precisely on where I am. If I'm this side of the 7, I would need a force of 21.6, 7.6. If I asked you what happened this side of the 7, and just looked at the equilibrium of that, then I wouldn't include this 7. So it depends on which side. I said in the question, point just below C, so I said in the question that really what I was interested in was what happened like that. So in fact, this doesn't come into the equilibrium equation, of course. Okay, so the material beyond here, and all the load system beyond here, must be exerting forces like that and that on this piece, so this piece is in equilibrium. The next thing you do is you resolve these. You resolve this into two components, one down the slope and one at right angles to the slope. And you resolve this into two components, one down the slope and one at right angles to the slope. That and that constitute a compression.
Is that 18.5 not minus the horizontal component of that 7?
No, 18 point. There's only one horizontal force on this piece.
No, but the at B, surely that 7 will have a force, a horizontal force.
Ah, but yeah, but what I'm looking at, I'm looking
is that
at.
in total?
Yeah, it's the total before I resolve it. Yeah.
Right, okay.
So first of all, I resolve horizontally and vertically, and then I resolve those results into down the slope and at right angles to the slope. Okay.
Yeah.
I see what your problem is. So there we are. The first thing I do is work out what I would need horizontal and vertical forces to provide equilibrium, and then I resolve them along the slope and down the slope. And that enables me to get what is called N, which is the usual symbol for thrust, and S, which is the usual symbol for shear. Now, in the question, I'm not terribly interested in the shear. I put it in just for completeness. But obviously, if I'm going to design this piece of stuff, I've got to design it for a bending moment, and I've got to design it for a thrust, which is the sum of that and that. That's what constitutes the compression of the member. After that, it's just the usual procedure. The first thing you say is, well, because we'll have a problem with lateral torsional buckling, I better work out the lateral torsional buckling coefficients. In the question, I think you're given all the formula you need. Yes, bending, the effective length is L plus 2H. The critical stress is rho 1 beta squared diddle diddle, and you're given a table of H over B against beta 1. So the first part of it is to work out K crit, the buckling factor, because it's likely to do that as well as the effect of the axial load. So there's 10 marks actually for working out what the permissible bending stress is and what the actual bending stress is. In addition to that, there are axial effects due to this and this. And that's what the next 12 marks are all about. And then you stuff them in the magic formula that combines them, which is formula 6.35, to see what happens. It's almost impossible to set a timber question in which there isn't a little bit of statics first. But the statics doesn't go beyond what you ought to have learned in first year. You didn't do three-pin arch in first year, I bet. Yeah. Which of course means you've got plenty of time to forget it. So there we are. So everybody reasonably clear about that one? And in fact, I set one of these in January 2011. If you look underneath. it's a bit like playing. Playing one of the gambling games. how often are you going to get a picture card and an ace? And unless you're one of these very clever people who can count how many have gone, you know. But basically, the principle's very easy. You're more likely to bugger up the statics actually than you want to mess the rest up, because the rest of it, I give you all the formula and just ask you to substitute the numbers.
So even if we mess up the statics, we still get the rest right.
What I will have to do, which will annoy me no end, is I shall have to wade through the second half of the question using your silly figures from your statics to see what happens. Because, I mean, basically, you get marks for method rather than answer.
No, you're January 2011 page.
Sorry?
On your January 2011 paper,
Yeah.
you wrote any subsequent calculations based on incorrect values will attract half marks. You said that you only did that
well, let's
back
have a
in
look.
the day.
It had 11 marks for the statics. So let's assume that you got those wrong and you got sort of answers, but they weren't the right answers. Then you lost most of your 11 marks. We then see where it takes you, basically. If it takes you into something which is manifestly silly and you don't spot that it's manifestly silly, then I might penalise you for being daft. But otherwise, you, in theory anyway, you have the potential to pick up the remaining 8 and 8, 16 and 6s, 22 marks. Which I mean is why all these questions are a gift, because if I give you all the formula and all you've got to do is stuff numbers in them, it's really like an accountancy exam, isn't it?
So like, if you fail the first part and you try assuming these are the vertical values,
yeah,
and you get the rest right, would I get the full?
Provided, as I say, if in
reasonable.
the process of doing the rest you didn't get some answer that was so obviously stupid as to indicate that there was a mistake that you were daft enough not to spot. And so the
spot what's too go back.
Oh well, I mean, basically what you do is you say, oh, I have made a boo-boo. And you draw my attention to it, and I think, look, clever lad, and I give you 2 or 3 marks for doing that. What I don't advise you to do is then go right back to the beginning and turn it through our exam.
So if we make a mistake, we should note it and point out that we know it's...
Oh yes, if you make a mistake, point out that, and people do this on exam papers all the time, I've just realised that I've done so-and-so wrong, but I haven't got time to put it right. And I'll give you 2 or 3 marks for spotting that.
I'm just going to write, not doing the paper, just write everywhere.
What would happen then is you get sort of 3 marks for saying, well, what I just put down is a load of rubbish. So you get 3 out of 33, and you go on to the next question, and what I just put is a load of rubbish, and you get 3 out of 33. So yeah, I mean, it's... The object of the exercise is the university have made this quite clear to us, and made it quite clear to us about 10 years ago. The object of the exercise is for students to pass, irrespective of how incompetent they are, really, because the university likes the fees, and it doesn't like the prospect of being sued.
Why wouldn't we see you?
Oh, I've worked in many departments. I actually worked in the architecture department, where a student did sue the university.
That's a bit subjective, isn't it?
What, because they didn't pass?
No, he said that architecture's different from engineering. It's very subjective, and it's all studio based and so on and so forth. And he said he didn't get enough supervision and advice in the studio, and in fact he's quite right, he didn't. Basically because the studio instructor, because it's a very personal subject, didn't like him. So she spent all her time teaching the rest, and sort of every time he wanted, it's 5 o'clock, I'm on my way home. And basically, the reason he won his case in the end, and I was head of department at the time, and I advised him to sue you. The reason he won his case was that we couldn't produce documentary evidence to show that we taught him properly.
Oh, can I do it from a distinction?
Because I had written into the departmental regulations, not the regulations, that if a student failed in design, he was to be given a written explanation of why his work was inadequate, so that he would have a chance to put it right. Now, you haven't got this in engineering. You'll never get it.
Okay.
It doesn't matter.
But notwithstanding, the principle still applies that the university does not like
Master, I think.
high failure rates. It can be two-edged. I mean, I've spent over 40 years teaching before I retired. And somewhere towards the end of my career,